So in this video, we're going to look at analytically finding the limit of a rational function, and we're going to do it in the case where the denominator of the rational function is undefined at the value for which we're taking the limit. So the first step is we're going to take the limit as x goes to 2 of this rational function. We have the ratio of two polynomials. You want to look at the number at which you're taking the limit, and you want to mentally plug that number into your denominator. And if it causes a division by 0, you're going to identify that you're not going to be able to use this tool for this particular limit. In the previous video, we were able to take the limit of the ratio being the ratio of the limits, but that was because we didn't get a limit of 0 in the denominator term. And so in this case, if I plug in 2 and get a 0, this indicating to me that when I take the limit on x minus 2, I'm probably going to get a 0. So I'm going to have to do something different. So the first step is the same as it's been in the previous videos. You rewrite the problem in your own handwriting if you want full credit on homework and exams. So rewrite the problem: x squared minus 3x plus 2 all over the x minus 2. So step 2 is, when we're working with a rational function, you want to factor the polynomials. The denominator is already a linear binomial, so I don't need to worry about factoring it. But here I have a second degree polynomial in the numerator, and I want to see if it will factor nicely for me. So I'm going to take the limit as x goes to 2. I want to try to factor that numerator. And in this case, I'm going to get x minus 2 times x minus 1 is how the numerator will factor, and this is all over x minus 2. And then what you want to do is look at the factors, the binomials in the numerator, the factors, and look and see if one of them will cancel with the factor in the denominator. And so we're going to recognize that x minus 2 divided by x minus 2 equals 1 as long as x is not equal to 2. And in this case, x isn't going to be equal to 2 because we're taking the limit as x gets as close to 2 as we want, but we're not letting x equal 2. So I'm going to do the simplification, which is going to give me the limit as x goes to 2 of 1 times x minus 1 is just going to be x minus 1 in parentheses because I'm taking the limit of both terms. And then when I get it to here, I recognize I have the sum or difference of two functions. So I'm going to break it into two pieces like we've done in the previous videos, where we take the limit as x goes to 2 of x minus the limit as x goes to 2 of 1. And now I have the limit as x goes to 2 of x. So this corresponds to this tool right here. The limit as x goes to 2 of x will equal 2. So we get 2 from that limit minus, here I have the limit as x goes to 2 of a constant. So that's this first tool here. The limit as x goes to 2 of a constant will just equal the constant. So we get 1, the constant, coming down, and 2 minus 1 is 1. So the limit as x goes to 2 of this rational function is just equal to 1. So this is the first possibility. The first possibility is where when you factor the numerator, you get the denominator to cancel for you, or you get a 1 because you get x minus 2 divided by x minus 2. I guess canceling is kind of a naughty term. So the next example is going to play out just a little bit differently. So you still do the same thing that we did in the on the previous slide. You look at the number at which you're taking the limit, which in this case is 2. And we notice that if we plug 2 into the denominator, we get a division by 0, which means this tool isn't going to be available to us for this problem. So we start off again by rewriting the problem in our own handwriting. The limit as x goes to 2 with this x goes to 2 exactly under the limit symbol here. It doesn't go under the function. The function is off to the side. We get x squared minus 4x plus 3 all over x minus 2. And just like we did on the previous slide, we want to try to factor that numerator if we can. And in this case, it looks like it's going to factor as x minus 3 times x minus 1. And this is going to be over x minus 2. And just like we did in the previous slide, we want to look at the factors in the numerator and see if there is a factor that will cancel with the factor or binomial in the denominator. In this case, there isn't. We don't have an x minus 2 in the numerator to cancel the x minus 2 in the denominator. So that tells us when we graph this function, we're actually going to get at 2, we're going to get a vertical asymptote. The rational function will be undefined, and it will be going to plus or minus infinity. It'll be sweeping up along its vertical asymptote. So this is going to tell us that the limit is not going to exist. So the limit does not exist, and that's because we have a vertical asymptote at x equals 2.